Thank you for the opportunity to talk about the use of machine learning in engineering. I'm Paolo Gardoni. I'm the Alfredo Eng Family Professor in the Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign. I also serve as the editor-in-chief of the journal Reliability, Engineering, and System Safety, published by Elsevier, and I'm the founder and former editor-in-chief of the journal Sustainable and Resilient Infrastructure, published by Taylor and Francis. My research interests include probabilistic mechanics, reliability, risk and life cycle analysis, decision-making under uncertainty, performance assessment of deteriorating systems, modeling of natural hazards and societal impact, and optimal strategies for natural hazard mitigation and disaster recovery. I will talk about intelligent construction, and in particular about machine learning in civil engineering. There are two parts in my presentation. First, I will introduce what machine learning is, and then I'll give you some example of applications specific in civil engineering. So let's first introduce machine learning. Machine learning teaches computers to do what comes naturally to all of us, which is learn from experience. Machine learning is great for complex problems involving a large amount of data with lots of variables, but no existing formula or equation that describes the system. Some common scenarios where machine learning applies include when the system is too complex for handwritten rules, like in the case of face and speech recognition. When the rules of a task are constantly changing, like in the case of fraud detection. And when the nature of the data itself keeps changing, like in automated training, energy demand forecasting, and predicting shopping trends. Machine learning uses two types of techniques: unsupervised learning, which finds hidden patterns in the input data, and supervised learning, which trains a model on known input and output data so that it can predict future outputs for given inputs. Unsupervised learning draws inferences from datasets that don't have labeled responses associated to the input data. Clustering is the most common unsupervised learning technique, and it puts data into different groups based on shared characteristics of the data. Clustering is used to find hidden groupings in applications such as gene sequence analysis, market research, and object recognition, among many other applications. On the other hand, supervised learning requires each input data to come with a correctly labeled output, a corresponding output. And it uses these labeled data along with classification and regression techniques to develop predictive models. Classification techniques predict discrete responses, like whether an email is genuine or spam. Essentially, this model classifies input data into a predetermined set of categories, while regression techniques predict continuous responses, like what temperature a thermostat should be set at or fluctuations in electricity demand. Again, the big difference here between supervised learning and unsupervised learning is that supervised learning requires correctly labeled examples to train the machine learning model and then uses the model to label new data to predict new output for a given input. So keep in mind the techniques you use and the specific algorithms you select depend on the size and type of data you're working with, depend on the insights you want to get from the data, and how those insights will later be used. A supervised learning algorithm takes in both a known set of input data and corresponding output data, and it then trains a model to map inputs to outputs so it can predict the response to any new set of input data. And as we have previously discussed, all supervised learning techniques take the form of either classification or regression. Classification techniques predict discrete responses, and you can use these techniques if the outputs you want to predict can be separated into different groups. Examples of classification problems include medical imaging, speech recognition, and credit scoring. Regression techniques, on the other hand, predict continuous responses. A good example of this is any application where the output you're predicting can take any value in a certain range, like in the case of the stock prices and acoustic signal processing. Now, say you have a classification problem you are trying to solve. The logistic regression algorithm is then one of the simplest methods. It is used with binary classification problems, meaning problem where there are only two possible outcomes, and it works best when the data can be well separated by a single linear boundary. And keep in mind that there are many other classification algorithms, and this is just one of the most common. There are also plenty of algorithms to choose from if you have a regression problem. Linear regression is a statistical modeling technique. You can use it when you need an algorithm that is easy to interpret and fast to fit, or as a baseline for evaluating other, more complex regression models. Nonlinear regression helps describe more complex relationships in the data. You can use it when the data has a strong nonlinear trend and cannot be easily transformed into a linear space. Again, these are just two common regression algorithms you can choose from. There are many more you might want to consider. A Bayesian approach specifically is ideally suited for many engineering applications because it allows us to use all types of information that might be available. They range from engineering judgment up to objective data from the field or from the laboratory. Next, I would like to give you some examples where we have used machine learning specifically for civil engineering applications. Our goal as civil engineers is to develop safe, sustainable, and resilient infrastructure. Infrastructure provides vital services that support and enable societal functions, and ensuring the reliability and resilience of infrastructure is critical for public well-being. We need to increase the resilience then, or the reliability, the functionality, and reduce the duration and frequency of service disruption. Bridges, for example, are critical links in the transportation infrastructure. And past disasters have shown that bridges are particularly vulnerable to natural hazards. I'm showing here some examples of damage to the transportation infrastructure due to earthquake and hurricanes. So fragility functions are commonly used to estimate the vulnerability of bridges subject to hazards. For example, let's consider a reinforced concrete bridge, like the one I'm showing here, subject to an earthquake ground motion. We're then interested in computing the fragility of the bridge, which is defined as the conditional probability of attaining or exceeding a specified damage state for given measures of the demand, which in this case are given measures of the ground motion intensity at the site of the bridge. So there are three fundamental steps in developing fragility functions. First, we need to construct probabilistic capacity models that tell us for the given geometry and material property how much forces and deformation, for example, will each column be able to sustain before failure. Then we need to construct probabilistic demand models that give us the shear and the deformation demand that each column will be asked to sustain for a given ground motion. And we need to do this for every column in the bridge. And finally, as a third step, we can conduct a rigorous reliability analysis combining the probabilistic capacity models and the probabilistic demand models to estimate the conditional probability for the bridge. Now, machine learning can be used to efficiently develop the probabilistic capacity and demand models that are needed to construct the fragility functions. Also, infrastructure suffer from aging and deterioration over time. Aging and deterioration might considerably reduce the service life and reliability of infrastructure. They are becoming a growing problem for all types of infrastructures in the US and everywhere else in the world. And they are making damage data from past events, when there was less deterioration, less informative, making empirical fragility function not very helpful. Infrastructure might be subject to multiple deterioration mechanisms like corrosion, alkali-silica reactions, or even past seismic damage. And changes in the material and geometry due to these deterioration processes can then lead to higher vulnerability of the bridges or the infrastructure to multiple hazards, which means higher fragility curves. Specifically, the effects of corrosion are found to be very severe for post-tension concrete bridges. Now, post-tension concrete bridges are a special type of concrete bridges that are gaining acceptance and use around the world. post-tension bridges have many advantages. They have an improved constructability and shorter construction times, an improved sustainability, a higher flexibility in the geometric design, and overall, they are more economical than other bridge types. Now, to understand why they are so vulnerable to corrosion, we can look at how they're constructed. First, the piers and the end segments are erected, and then the remaining segments in between piers are kept in place using temporary support systems. When all these segments are in place, strands are placed through all the segments. I'm just showing here some segments so you can see the strands. And then the strands are stressed or post-tension to keep the segments in place. However, the presence of many unwanted void inside the ducts that protect the strands can lead to accelerated corrosion, making bridges very vulnerable to deterioration. So far we look at how machine learning is able to incorporate the rule of physics and mechanics in the performance and in the fragility, the probability of failure of bridges. We also saw how we can use machine learning to incorporate the effects of aging and deterioration. Now we can also use machine learning to incorporate information from the recovery and mitigation strategies, which I didn't discuss in details. And also, machine learning can be used to incorporate information from structural health monitoring and non-destructive testing that provide information on the actual state of the structure over time. Now, so far I was talking about failure of bridges subject to earthquake ground motions. However, scour, which is the erosion of the foundation around the piers, is found to be one of the leading causes of bridge failures, not necessarily earthquakes. So machine learning can be used to assess the structural capacity and demand of column subject to scour, just like we saw earlier in case of earthquake ground motions. And similarly, we can look at vehicle collisions, which is another leading cause of bridge failure. Machine learning can be used to assess the structural capacity and demand of columns subject to large vehicles, and then estimate the probability of failure. So, in conclusion, machine learning can be a powerful tool in several engineering applications. We introduce two types of analysis. Unsupervised learning is one. Unsupervised learning finds hidden patterns in the input data. The other one is supervised learning, which trains a model of known input and output data so that it can predict the future outputs for given inputs. Civil engineering can use machine learning in several ways. One example I presented today is to develop probabilistic models that predict the future response of structures. And in particular, we saw that machine learning can be used in predicting the probability of failure of bridges by providing models for the probabilistic capacity and demand of a bridge. Machine learning can also be used to consider the effect of aging and deterioration, to consider the recovery and mitigation strategies, and to include information from structural health monitoring and non-destructive testing. I gave you some examples focusing on seismic excitations, but machine learning can be used in the very same way, also considering other hazards like scour and vehicle collision, just as two examples. Many articles on machine learning can be found in the journal Reliability, Engineering, and System Safety. In fact, we recently published a collection of articles on physics-informed machine learning for reliability and safety. If this is a subject of interest to you, I encourage you to look at this collection of articles. There are other references I'd like to bring to your attention. These are 6 books that I co-edited and then include much of what I presented today and many more details. Thank you again for the opportunity to talk about the use of machine learning in engineering. Unfortunately, I could not be there in person. However, I hope this video was helpful, and I hope to have an opportunity to meet all of you in person in the near future.